Picture, if you will, a world shrouded in a fiery cataclysm. 65 million years ago, the Earth bore witness to an apocalyptic spectacle that forever altered the course of life on this planet. In the heart of the Yucatan Peninsula, an asteroid of colossal proportions, some 15 kilometers in diameter, hurtled through the cosmos on a collision course with our ancient home. As it breached the atmosphere, the heavens themselves seemed to ignite, bathing the landscape in searing flames. In an instant, a maelstrom of heat and destruction unfurled. Enveloping everything within a staggering 1,600-kilometer radius. The creatures that gazed upon this cosmic inferno were consumed by its wrath, reduced to mere ashes in the blink of an eye. This cataclysmic event, etched into the annals of time as the KT extinction, claimed the lives of nearly 70% of Earth's living beings, most notably the long-lived dinosaurs. In its wake, a colossal scar etched into the Earth's surface, a testament to the unimaginable power of celestial forces, a crater spanning 180 kilometers in diameter and plunging to a depth of 20 kilometers. This event, one of 5 harrowing mass extinctions in Earth's storied history, stands alone as the sole cataclysm caused by an interstellar visitor, a messenger from the boundless expanse beyond. But here we stand, in an age of discovery and innovation, pondering a question of cosmic consequence. What if, once again, the specter of a formidable asteroid loomed on our horizon? Since we don't have Superman as a shield, could we avoid the same fate that was met by the dinosaurs? Or would we be powerless to stop such a catastrophic event? So, a fairly large asteroid is on its way to colliding with the Earth. What can we do to prevent this? Well, firstly, before we can do anything, we must determine the nature of the asteroid itself. This will help us find the best course of action and minimize any potential damage. In general, the asteroids in our solar system are situated in 2 areas, the inner and outer asteroid belts. The smaller inner belt, referred to as the main belt, lies between the orbits of Mars and Jupiter. The outer belt, the Kuiper belt, is much larger and lies beyond the orbit of Neptune, which is primarily composed of comets. Asteroids are rocky remnants from the solar system's formation, approximately 4.6 billion years ago. Within the inner belt, asteroids can range from just a few meters to several kilometers in diameter, though the total combined mass of these is less than the Moon. Asteroids are mostly made up of rock, but some are made up of clay and silicate as well as different metals, such as nickel and iron. According to NASA's asteroid data, we know of over 1 million objects, and approximately 26,000 of those will pass near Earth and are subsequently named NEOs, or near-Earth objects. About 2,000 of these near-Earth objects are potentially dangerous, of which between 100 to 200 have a diameter of over 1 kilometer, larger than any man-made structure on Earth. These huge asteroids would pose a significant threat to life on Earth. However, should we be seriously concerned about any of these? We shouldn't lose sleep over an asteroid hitting the Earth anytime soon, not just yet anyway. We are currently living in one of the most peaceful times the solar system has ever seen. This was not the case 4 billion years ago. Back then, asteroid strikes were commonplace in our solar system. We know that by just observing the Moon and the many craters on its surface. However, unlike the Moon, which is still bombarded by tiny micrometeorites due to the lack of atmosphere, the only asteroids that reach the Earth's surface are ones that aren't burned up by the atmosphere. The Earth currently has a 2-stage defense against most asteroids. Firstly, most potentially dangerous objects in the inner asteroid belt are hoovered up by Jupiter due to its immense gravitational pull. Secondly, Most small and medium-sized asteroids are burned up in the Earth's atmosphere and never reach the surface in the first place. But what if a large object, such as certain NEOs, gets through this defense? What about an asteroid several kilometers in diameter, like the one that killed the dinosaurs? Well, asteroids of this size are only expected to hit the Earth once every 100 million years, so we have tens of millions of years to go before we can expect one of those. Although, as mentioned previously, there are many asteroids near Earth that have the potential to cause significant destruction. Early in the Earth's history, the surface was pulverized by many objects as the atmosphere was nowhere near as thick as it is today. During the late heavy bombardment, which took place 3.8 to 4.1 billion years ago, rocky leftovers from the early solar system were constantly bombarding the planets. Some of the asteroids that impacted Earth during this period were believed to be enormous, much larger than even the ones responsible for wiping out the dinosaurs. However, we can't say that it's always been bad news for the Earth when an object has collided with our planet. It is theorized that asteroids themselves were responsible for the atmosphere that largely protects us from them today. Even our moon wouldn't have existed had a large body not collided with the Earth, so we have to be somewhat thankful for them. Asteroids are, in a way, the universe's delivery system. Okay, now that we understand the nature of most asteroids, the next step would be to detect any incoming threats before they get dangerously close. We have a variety of ways to do this. The first method would be to actually see these objects via the many telescopes we have available to us. Using these, we can detect large asteroids well before they come anywhere near Earth. Another method of detection is the use of radar, though this is usually reserved for those asteroids that have gotten a lot closer to our planet. Using radar, we can determine the composition of any close asteroid, and knowing this will help us determine what kind of explosion may ensue as it enters the Earth's atmosphere. Also, fortunately for us, at the University of Hawaii, a system named the Asteroid Terrestrial Impact Blast Alert System, or ATLAS for short, has been set up with one objective in mind: to save Earthlings from incoming space rocks. ATLAS consists of 2 telescopes in Hawaii, and they aim to expand this to 4 with 2 more somewhere in the southern hemisphere. The system currently has 4 half-meter telescopes, and each telescope can image a swath of sky 100 times larger than the full moon in a single exposure. It is equivalent to the light of a match flame in New York viewed from San Francisco. ATLAS therefore scans the visible sky in much less depth, but much more quickly, than larger surveying telescope arrays such as University of Hawaii's Pan-STARRS. Pan-STARRS goes approximately 100 times deeper, but needs weeks instead of a quarter of a night to scan the whole sky just once. This makes ATLAS better suited to finding small asteroids which can only be seen during the few days that they brighten dramatically when they happen to pass very close to the Earth. Also, NASA utilizes a whole network of telescopes both on the ground at observatories and space telescopes, as well as data collected by independent star watchers to determine the path of any object that has gotten close to the Earth. Most of the time, near-Earth objects pass the Earth without any issue. However, we still miss many asteroids even with all the detection equipment at our disposal, albeit large objects are hard to miss, though not impossible to miss. One such example was the 2013 Chelyabinsk meteorite. Date was February 15, 2013 at 9:20 a.m. local time. 19 meters in diameter and weighing 12,000 tons, an asteroid was speeding towards Earth at 65,000 kilometers per hour. It entered the Earth's atmosphere over Siberia, Russia. That was the asteroid that we did not detect, which ended up exploding in the atmosphere. No one was killed, but almost 1,500 people were injured and caused an estimated $33 million in property damage, as the resulting shockwave damaged thousands of buildings and scattered fragments of the object over a vast area. So now that we know how we would spot an incoming asteroid, now we get to the good part. How would we stop it? The first method of defense we have, or one that we'd like to develop in the near future, is asteroid deflection via kinetic impact. This would involve actually redirecting the asteroids headed towards the Earth by using the kinetic energy of an object to intercept the asteroid. In 2022, NASA launched what it called the Double Asteroid Redirection Test, or DART for short. NASA called this the world's first planetary defense technology demonstration, testing a technique of asteroid deflection using a spacecraft. This basic idea was to launch this spacecraft to smash into an asteroid and change its trajectory. The target was an asteroid moonlet named Dimorphos, a small celestial object 160 meters in diameter, which orbits another larger asteroid 780 meters in diameter, named Didymos. Neither of these two asteroids posed any threat to the Earth. By smashing the spacecraft into Dimorphos, NASA confirmed that the asteroid's orbit around Didymos was altered by 32 minutes, shortening the 11-hour and 55-minute orbit to 11 hours and 23 minutes. The mission was a success and confirmed that we can indeed successfully navigate a spacecraft to intentionally collide with an asteroid to change its orbital path. This is very encouraging, as it means if we were ever faced with an unavoidable collision with an asteroid of similar size that was believed to cause widespread devastation to populated areas, we could simply swat it away like an annoying fly. Another method we could utilize, and is probably the first that comes to mind for many people, is blowing up any object unfortunate enough to come close enough to a planet populated by humans. We could do this by launching a nuclear warhead at it. However, it should be noted that the detonation of any nuclear device in space is prohibited by the Outer Space Treaty of 1967. But for argument's sake, let's say we ignore that for a second. Would nuking an incoming asteroid be possible? Well, yes, if the nuclear weapon you launch is sufficiently powerful. However, we'll then have two problems to deal with instead of one. Firstly, if the asteroid is a larger one, it would likely break, and the pieces of debris would rain down below. Secondly, the nuclear fallout from the bomb itself may have devastating effects, such as severely damaging electrical equipment and nearby satellites, as well as radioactive fallout spreading over a large area due to air currents. NASA research has also shown that deflection is more effective than destruction. To achieve this using nuclear weapons, we would ideally need as much warning time as possible, likely several years. The more warning time provided, the less energy will be necessary to divert the asteroid just enough to adjust the trajectory to avoid Earth. The best way to divert an asteroid through deflection via nuclear weapons is by adjusting the output of neutron energy in the nuclear explosion. So nuclear weapons may be very effective against smaller asteroids, but not as effective and may even cause more problems than they would solve against larger objects. Another downside is that nuclear weapons are very expensive, so there is a cost issue as well. Another alternative to explosive deflection is to move the asteroid slowly over time, rather than smashing something into it and moving it as soon as possible. Utilizing this method would in most cases require identifying a potential threat well before it got close enough to cause damage. But if we could, this method has many advantages. How this would work would be similar to an actual tractor. A small but constant amount of thrust accumulates over a period of time to deviate an object sufficiently from its course. Using a massive unmanned spacecraft hovering over an asteroid to gravitationally pull the asteroid into a less threatening orbit. Though both objects are gravitationally pulled towards each other, the spacecraft can counter the force towards the asteroid by utilizing an ion thruster, which would result in the asteroid accelerating towards the spacecraft and being slightly deflected from its original orbit. While this process is slow, this method has the advantage of working irrespective of the asteroid's composition or spin rate, as asteroids that are essentially large piles of rubble would be difficult to deflect by means of nuclear detonations, while a kinetic impact spacecraft would be inefficient to mount on a fast-rotating asteroid. However, a gravity tractor would likely have to spend several years beside the asteroid to be effective, so potential threats will have to be identified as soon as possible for this method to be effective. Ion beam shepherd, IBS, is a concept that uses a beam of quasi-neutral plasma to modify the orbit of a spacecraft or other orbiting body. The IBS spacecraft has an electric propulsion system that generates the plasma. The plasma beam is directed at the target object, usually space debris, to create a force or torque on it. The ion beam interacts with the target, exerting a net surface force and transmitting momentum to it. This method is similar to that of the gravity tractor. However, the advantage of this method is that a light spacecraft can be used, as it does not need to make contact with the asteroid. Rather, the spacecraft just needs to house a low divergence ion thruster pointing at the asteroid to divert it. The potential disadvantage of this is that if equipment fails or ends up being damaged, it may be very expensive to get the spacecraft back to Earth for repairs, as it would only be effective against potentially dangerous objects that are far away. The idea behind this method is simple: to blast incoming asteroids with powerful lasers to vaporize larger, dangerous asteroids into smaller, less dangerous ones, or even vaporize them away completely. The Directed Energy System for Targeting of Asteroids and Exploration, or D-STAR project, proposed by researchers at the University of California, D-STAR is a modular phased array of laser amplifiers. Design requirements are established by seeking to vaporize the surface of an asteroid with ejected material, creating a reaction force to alter the asteroid's orbit. A proposed system goal would be to raise the surface spot temperature to more than 3,000 Kelvin. Engagement distance required for successful diversion depends on the asteroid's mass, composition, and approach velocity. Distance to focus and desired surface spot temperature then determine laser array size. Volatile-laden objects, approximately 100 meters wide, approaching at 5 kilometers per second, could be diverted by engaging at approximately 0.05 astronomical units, requiring an array of approximately 100 meters side length. Phased array configuration allows multiple beams. A single D-star would be capable of targeting several threats simultaneously. An orbiting D-star could serve diverse scientific objectives. This would therefore be useful beyond its asteroid ablating capabilities, as the issue of increasing space debris is a problem we will most definitely have to tackle eventually. However, the construction of such an apparatus would require us to tackle many engineering hurdles. Mainly, just how would this giant laser be powered? One idea that's been proposed to tackle the power issue is to build an accompanying space-based solar-powered satellite covered in solar photovoltaic panels. However, this would be an insanely expensive undertaking, though some would argue that it would be a necessary one. This method involves deflecting an asteroid by focusing solar energy onto its surface to create thrust from the resulting vaporization of the material. For this to work, it would require the construction of a space station with a system of large concave mirrors similar to those used in solar furnaces. The main advantage of this method is that if everything is already in place, we would not require prolonged warning time, therefore being useful in emergency situations where an object has come dangerously close to the Earth. The system would intercept an incoming object and act as a giant magnifying glass, utilizing focused solar energy to eject material from the asteroid, which would act as thrust and alter its trajectory. The main issue with this method is that it is solely dependent on solar energy from the sun, so would only really be useful with targets smaller than itself, as they would be less likely to cut off the sunlight being received by the space station. To construct a space station largely made of solar panels would be very costly, as solar panels are expensive as it is without having to launch them into space, and there would be the troubling issue of the station being rendered useless when faced with larger objects. It may be an inefficient use of effort and resources when your defense system is only useful in certain situations. A mass driver is a system that physically lands on the asteroid and begins to eject material from it into space, manually decreasing the object's mass and slowly pushing it away from the Earth. This essentially uses the asteroid against itself in order to avoid a collision. The concept of mass driver deflection is enabled by a new spacecraft concept called Area of Effect Softbots, AOES, which have been developed under support from the NASA Innovative Advanced Concepts program. AOES are soft robotic spacecraft with large actuated surface areas as pictured, which allows for unique mobility and surface anchoring through contact electroadhesive forces. The ability to anchor regardless of the asteroid's subsurface structure enables the possibility of digging and launching material from the surface of a small NEA. By controlling when we launch the material from the surface, and by repeating this process for a period of time, we can produce measurable changes to an asteroid's orbit and thus could conceivably be used as an asteroid deflection option given enough warning time. This process is not fast, but could be very effective if implemented correctly, as we would be utilizing technology already available to us and equipment that has been used in many space missions. Lastly, this would be the most straightforward method of asteroid defense and would involve attaching a standard space engine to an asteroid and deflecting it. The advantage of this method is that it would involve utilizing technology that we have used for several decades, and we know very well how this equipment works and how to fix it if anything were to go wrong. We would essentially transform an asteroid into a rocket and redirect its original path to one away from the Earth. The main issue is whether this would even work, as rockets launched into space are far lighter than a large asteroid as they need to be to gain enough velocity to escape the Earth's gravitational pull. An in-space rocket engine that is capable of imparting an impulse of 10 raised to the 6 power newtons per second will have a relatively small effect on a small asteroid that has a mass of roughly 1 million times more. This would work in theory if the asteroid was quite some distance away from the Earth, but a rocket engine needs fuel to function, and supplying enough fuel for this to work may pose a legitimate logistic issue. There have been many other proposals that have been discussed, other than the 7 methods we have discussed. These involve the use of solar sails, which would utilize the power of photons from sunlight to push an incoming asteroid away from the Earth, deflecting a potential impactor by releasing a cloud of steam in the path of the object, hopefully slowing it down gently, and even magnetically stopping and/or capturing objects that contain high amounts of meteoric iron by deploying a giant coil of wire in its orbital path. So in conclusion, there are many methods we could use or develop to defend ourselves from giant space rocks that are dead set on potentially wiping out most, if not all, life on Earth. Which methods we end up turning to largely depends on the properties of the asteroid that is hurtling towards us and the time we have to act. Should we be losing sleep over a massive rock colliding with the Earth? Probably not. Well, not just yet anyway. However, humanity will eventually have to tackle this problem, so it is important that we conduct tests such as DART and have plans in place when the inevitable comes. Because it is not a question of if, but when.